Chapter 1 Fundamentals of Thermodynamics, Section 1.6 Pure Gases, Liquids, and Solids. In the ideal gas model, particles do not interact with each other. There is no attraction or repulsion between gas particles. However, real gas particles, they do interact with each other. They attract and repel each other simultaneously. For example, two helium atoms may repel each other and attract each other at the same time. How is that possible? Let's look at two helium atoms. We have a helium atom on the left, a helium atom on the right. They both have a positively charged nucleus and two negatively charged electrons. Now we can tell this nucleus and this nucleus repel each other. There are four electrons, they repel each other. At the same time, this nucleus is attracted not only by these two electrons, but also by these two electrons from the other helium atom. Therefore, we have attraction, we have repulsion. They both depend on the distance between these two helium atoms. When the distance is shorter, we have stronger attraction and repulsion. At the same time, when the distance is longer, we have weaker attraction and weaker repulsion. And because atoms repel each other, and this repulsion is due to the repulsion between the nuclei and also the repulsion between the electrons. If we try to squeeze two helium atoms toward each other, there's going to be a huge repulsion. That means each helium atom will have to occupy a certain space. And now we're going to use a numerical example to estimate the space a helium, but in this case, argon atom occupies. We're going to estimate the volume of an argon atom given its van der Waals radius. R is 1.88 angstroms from literature, and we're going to estimate the density of solid argon with a face-centered cubic crystalline structure. So first, let's calculate the volume of one argon atom. We're going to assume this argon atom has a spherical shape. The formula is, 4/3 times pi r to the power of 3. And we plug in the value of r. 1.88 angstrom is 1.88 times 10 to the power of negative 10 meters. We do the calculation, the result is roughly 3 times 10 to the power of negative 30 cubic meters. Now if we imagine compressing 1 mole argon gas particles into the solid phase with a face-centered cubic crystalline structure with 74% closest packing efficiency, then we can calculate the volume. So first we have the volume of one argon atom, which is a sphere, multiplied by the Avogadro constant, and then divided by the packing efficiency. We'll be able to get the total volume of 1 mole argon in the solid phase. We got 22.6 milliliter. The density of solid argon can be calculated because we know the mass of 1 mole argon, we know the volume of 1 mole argon based on this calculation, and then we get the density 1.77 gram per liter. Let's compare this with literature value 1.68. These two values are really close to each other. Another numerical example, let's say we know the density of solid xenon, 3.64 gram per milliliter. And now we're going to estimate the van der Waals radius of the xenon atom. So first, the volume of 1 mole solid xenon with the face-centered cubic crystalline structure with this much packing efficiency is over here. So we have, this is the molar mass. It's from the molar mass of xenon. We're assuming 1 mole of xenon, so it's 131 grams, and we have the density of xenon. And now we have the volume of 1 mole xenon, 36 milliliters. Or we can say the molar volume of solid xenon is 36 milliliters per mole. And now we can compute the average volume of an individual xenon atom. So first we have this packing efficiency. So we have the molar volume times the packing efficiency, and then divided by the Avogadro constant, we get the volume of one single xenon atom. Now we assume this atom is spherical, and then we use this equation for the volume of a sphere, 4/3 times pi times the radius to the power of 3. We set it to be this volume. We can compute the radius of a xenon atom. It's 2.2 angstroms. For comparison, the literature value is 2.16 angstroms. Again, these two values are really close to each other. Another example. This time we'll estimate the van der Waals radius of water molecules. So obviously a water molecule is not spherical. It does not have a spherical shape. But still we can estimate its van der Waals radius as if it were spherical. For example, we can estimate the van der Waals radius of water is estimated to be 1.4 angstroms given the density of ice. How do we get this number? How do we calculate the van der Waals radius of water? Again, it's pretty simple. If we know the density of ice is 0.92 gram per milliliter, and we know the molar mass of water is 18 grams per mole. From these two pieces of data, we can get the molar volume of water. It's roughly 20 milliliters. And then 20 milliliters for 1 mole water molecule multiplied by this 34%, we get 6.8 milliliters. And this number divided by the Avogadro constant, we will be able to get the volume of one individual water molecule. Now we're going to assume it's spherical. Again, we're going to use this equation. 4/3 times pi r to the power 3 is equal to the volume of one water molecule. From this equation, we'll be able to calculate the van der Waals radius. Over here, if you click this, it's going to bring you to a Wolfram Alpha page that shows you the whole calculation. And also you can just go to this wolframalpha.com and type up this equation. Again, this is a molar mass, this is density, this is packing efficiency. And why do we have this? Well, this is for unit conversion, and this is Avogadro constant, and this comes from the equation for the volume of a sphere. Again, this is just an estimate of the van der Waals radius for a non-spherical molecule such as water.